Just a reminder that for project, by the way, how many of you are already done with project 2? Okay, that's good. Yeah, so just a reminder that please implement stack adjustment correctly for project 2 as I described previously, because if you don't do that, it may potentially work, but it doesn't mean that it's correct, right? So that's just letting you know. So please make sure you subtract 4096 from your stack to get a physical address, and when you get the virtual address, you add this 4096 back. That I already covered in lecture 20. Because sometimes if you don't do that, it may just be, especially if it's for your physical address, it may get lucky and point, so to say, right, get lucky and still point to some page, but that's not the page that you want to use. So just be sure you adjust it in both cases, in both physical and virtual address. So last time we talked about data races and race conditions. Can you remind me what's the difference between a race condition and data race? So what is the fundamental difference? I mean, those terms are often used interchangeably, but they're not exactly the same. Oh, did somebody want? Okay, go ahead.
Data racing is when two threads are kind of, competing with each other, doing the same process at the same time.
Okay.
This condition is when there's a possibility where multiple threads could have an inconsistency.
So data race is when you incorrectly trying to change the memory location or something like this, and the race condition is the actual error in your program, which may be caused, frequently it's caused by the data race, but may also be caused by some other issues. Sometimes we saw that we can have 0 data races, but still have race conditions. So also recall that we had this mutual exclusion approach. So for the mutual exclusion approach, we said, okay, the simplest one is to disable interrupts. But that's not great because it only works on uniprocessor systems. And even for uniprocessors, that's not ideal. So then we looked at some software-based solutions such as Peterson's lock and Bakery lock. And do you see any disadvantages of software-based approaches? Do you remember what the disadvantages are? I mean, because why do we need any hardware-based solutions if like everything is fine if you can solve it by software? Any idea? There were 2 problems. So first problem with the software-based approaches was that so it doesn't work on modern architectures because it requires sequential consistency, and even though you can implement sequential consistency on modern architectures, it's not that cheap, right? So and at that point, it's really not worthwhile to use that logs. By the way, can you hear me well? Okay. Yeah, so the other problem was that and I think the first problem is more like a practical issue, but the other problem was somewhat also practical issue, but something that decreases usability of these logs. So for the software-based approaches, we effectively need O of n memory. So let's say I have 100,000 processes in my system, and I need to know in advance that I'm going to have 100,000 processes. Not to mention that, that maybe it's going to be larger than this. Why it should be 100,000? You know, maybe it's going to be 1 million. But even if I just say, okay, that my worst case is 100,000, that would be a lot of memory for each log. So I have to allocate a slot for every single thread, right? And you know, so and performance can also suffer because of this. I have to check all these threads. But you know, what is the advantage of hardware-based approaches, such as those that use test and set, that we can just use all of one memory, and we don't need anything, you know, crazy. It just goes like replaces our incorrect algorithm with correct algorithm. So our initial incorrect algorithm was just setting a lock and checking it. But the problem was that there was a gap between setting a lock value and checking it. So with special hardware instructions, we can eliminate this gap and keep things simple. So next we will talk about pthreads lock API. So and how to use locks. Then also liveness conditions such as deadlocks and live locks, condition variables, pthreads API. There will be some more stuff later, and several synchronization problems. So not all topics will be covered today, but at least some of them will take a look. At least, you know, liveness conditions and how we use pthread locks. So those pictures you have seen before. So, you know, when you did your project one, you thought maybe I have a bug in my code and it's, you know, I have to spend a lot of time debugging it. But the good thing was that it was the same bug over and over again. So, you know, I mean, unless there is some special cases, typically you would run the program, it's gonna show exactly the same issue over and over again. So it's a different concern how to fix that, but you can easily reproduce it. So I guess it's pretty much the same for project 2, even though there might be some variability, but most of the time, if you have any issue, it will either crash or it will print an error. Now in real life, that's not, we don't always have that luxury that something fails and we can reproduce it easily, especially when we deal with concurrency bugs. So it may you maybe just pass and test one time when you are developing your software. Then once it's in production, you know, you realize there is some serious issues there. There is some race conditions, and you know those cause a lot of issues. And one particular example when it can be really bad, when we looked at this already, I think in some of the past structures, then when there is X-ray overdose due to a race condition. So because of race condition, the X-ray machine gave a high radiation, and that of course caused deaths. So that's a known issue. And another issue is that there was Northeast blackout of 2003. Also because of race condition, there was no alarms, you know, multiple day blackout, and then again deaths because of that. So I really hope that, you know, once you graduate and, you know, design some software, I mean, I always kind of joke that I hope that I won't need to fly a plane that my students wrote software, you know, like if you're developing software for airplane, I hope that it's going to be without race condition and so on, right? So because I mean this is actually another story, right? So you know there is some also issues, right? So maybe not because of race conditions, but there can be issues like that as well. So yeah, definitely you want to make sure that you don't make the same mistakes like people did in the past, because especially nowadays with multiple cores, we have more and more concurrency, so that's not going to be that unusual. So that means you have to be careful when you're developing software. Okay, go ahead. Well, I don't know. Well, I mean, let's see. I mean, I was working enterprise storage company, right? So developing enterprise storage. So I guess it's pretty much important stuff, right? Because if you lose data, that's bad, right? But you know, that was using multi-threading. So I think that is not guaranteed, right? Maybe in some cases, you can get away with this, but remember that even if you don't have multiple cores, we still have some concurrency in operating systems. You can still have interrupts coming, you can have signal handlers in processes, even on a uniprocessor, single process, you can still hit some issues. Just even if you just have one process and uniprocessor system, just one CPU, still there is a possibility to have interrupts, still there is a possibility to have some signal handlers in your program. So those things can still happen. Yeah, so anyway, I really hope that you study this topic well, and when you graduate, you won't have any significant concurrency bugs that will cause a lot of issues. Yeah, anyway, so another thing that I wanted to mention is the swap instruction. So last time we said we looked at test and set, and recall that test and set will return the old value, but it will also set the new value to true. So the swap instruction is different. So swap instruction is more general. It returns the old value, but it allows you to set your new value to anything you want, whether it's true, false, or maybe it's just some integer, or maybe some pointer. It's up to you. So the way that we can define swap is that the Boolean A variable and Boolean B, so there are two pointers. So, but there are those are two different pointers. A points to shared memory. So like maybe something like a lock or something like this. So something that has to be concurrent access by multiple threads. Whereas B is just a local variable. That means it's local to this specific thread. So B is used as an input and output parameter, so that B is on input will specify the value that we want to set, and on the output it will contain the old value that was observed. So effectively that will atomically retrieve the old value, set A to the new value, and store the old value in B. Again, only A is shared variable, B is just a local variable. So then you can implement a lock using swap. Let's say you set key is to true. So initial key is false. So lock is set to false. So now you're going to try to set lock to true. How are you going to do this? You pass this key to true, you set it to true, and while key is true, it's definitely going to be true on the first iteration. You're going to call swap. Swap on a lock. Lock is a shared variable, and key is the local variable. So that's just local to this thread. So you're trying on input to put true. It's always on input going to be true, and on output, you will retrieve the previous value of the lock. So initially, if no one has taken this lock before, you should get false. So that means the old value is going to be false, and the new value is going to be true. So this is how this thread was able to grab this lock, right? So now let's say another thread comes and tries to grab the same lock. The value of the lock is already set to true. So it will try to do swap with true again, but then the old value is still true. So true was changed with true, so that means nothing has changed. I mean, yes, you have written something to the memory location, but in terms of the value, nothing has changed. So therefore, you will continue again. You will, while key is true, you will try to do this operation again and again until the lock becomes false again. So once it becomes false, then one thread will be able to grab the lock and then enter the critical section. So yeah, so it's pretty much similar to test and set. The reason why I'm mentioning swap is because we have that instruction in x86. So in x86, it's known as exchange instruction. So in case you're wondering why do we have this instruction which exchanges memory location with some register, so this is why we have it. And it's done by default such that it can be executed safely concurrently. It's also possible to do some other instructions in x86 and like including things like adding or subtraction. You can also do that, but you need to specify a special prefix for that instruction. But exchange will work, I think by default it will already have a prefix. So this is how you can implement, like using pretty much the exchange instruction x86 to implement a simple lock. Okay, go ahead.
So function.
Yes.
Wouldn't two threads go to critical section? Because one of them set block to true and the other again set block to true.
Yes, but we check the previous value. Remember that the condition for to exit, the while key is true.
Key is local, you say.
Yes, but it's both input and output argument, right? For swap. So on input, you're gonna supply true. Always supply true on input. On the output, it can be both false or true, depending on the status of the lock. If the lock was not taken by anyone else before, the old value will be false. If the lock was taken by someone already, the old value will be true.
So two threads go to.
Yeah, so two threads go to the critical section. One thread comes, try to set the lock to true. So it was previously false, right? Because no one has taken it. So it tries to set it to true. Okay, it calls swap on the lock. On input, it supplies key true. On the output, it will get false. Because that's the
With void.
No, but B, the second argument is both input and output. Boolean B is the input and output, right? Yeah, so that's the second is local variable that is both input and output. So you on input, you're gonna put true, on the output, you're gonna get false because that's the previous value of the lock. So the second, so then it will go to the second iteration while loop and see that key is no longer true, so it will exit. The second thread will come, do the same operation, swap. I will try to do swap lock true, but then the previous value is already true. So then it will go to the second iteration of the while loop and so on. So the second thread will not be able to enter the critical section. So does it make sense? So that's kind of analogous to what we had with a simple lock, when we set the lock to 1 and then check the condition. The only problem with a simple lock that there is a gap between setting and checking the condition. So here we were able to eliminate this gap by just setting a new value and returning the old value.
So at one time we execute in atomic.
Yes, so it's going to be atomic, and it's not only just one instruction, right? On like on x86, but it's also synchronized across all cores. So if on multiple cores are trying to do that you still get a valid result. Okay, any questions? Okay. So in pthreads, we support locks. So we have like lock and unlock. I guess the only difference is that typically for user space programs, you don't want to busy wait. So in the previous example, we kind of busy waited. That means we're trying to get a lock. If you're unsuccessful, we try again and so on. So that is called busy waiting. So you're not doing any useful progress, but you just keep checking the log. So with pthread mutex lock, it will get descheduled. So if the thread cannot get a lock, it will get descheduled and probably we'll put it in a queue or something like that. And then only when the lock becomes available, it will take it from the queue and schedule the thread again. So in other words, this thread will not be consuming any CPU time. So it's actually both approaches are valid. For kernel space, we sometimes want to have busy waiting, and we want to have a so-called spin lock. So that means if the critical section is relatively small, the overheads for descheduling and scheduling again are pretty high. So we want to kind of busy wait. On the other hand, in user space, I mean, it's typically we don't do that, and for many reasons. One of those reasons is that what if you hold the lock and then you are preempted? So then no one else can get this lock, and you are not making any progress. So only when you are coming back, then you can unblock everyone else. So that is also an issue. In kernel, you have some control, you can disable preemption while you hold in spin lock, but not in user space. So therefore, in user space, we kind of prefer more like descheduling, only, pretty much. I mean, unless we have some special version of the lock. So also there is a tri-lock version. What is this? Is there any question? Tri-lock? Yeah, so tri-lock means it's like in previous case, if you cannot get a lock, you will get descheduled. So in the tri-lock case, you will try to get a lock, but if you cannot get a lock immediately, you will return as the error status. So that means we will not be waiting. So if I can do the swap operation from true to false, then I'm gonna complete it right away. Otherwise, I have to otherwise I'll just return an error and that's it. So let's take a look at the shared bank account example. So in this example, let's say we have wife transaction and husband transaction, and they're trying to both withdraw some amount from the bank account, and then we have to deduct this balance. So previously we didn't protect balance, right? So we would not have any locks, and that we know caused some issues. So we ran some program, and that we saw that it's actually can get inconsistent results. So what if we do a lock? So why will it solve the problem? Okay, go on. Yes, yeah, there is now mutual exclusion, right? Only one thread can do this operation. Only one thread is allowed to enter the critical section. And what is the critical section?
Balance minus equals.
Yes, yeah, balance minus amount, right? So that's the critical section. And because only one thread is allowed to execute the critical section, that is why it's going to be safe. So now let's take a look at the producer-consumer problem. So we previously found that this problem has some issues, right? So we have to protect count. So if we have, okay, so the straightforward way to solve it, we have lock mutex, and then we basically surround count with lock and unlock, right? Okay, that's fine. But will it be okay? Well, no, because we still have some operations that need to access count. So we need to sometime read count. And so what if we do while loop count equals to buffer size, or while count equals to 0? So, okay, so we can get a log there as well. Is there any problem with this example? Any ideas? Any guesses? Okay, go. Yes. So why is that? Can you give an example?
Because one process is waiting with the process.
Yeah, so let's take a look at one specific example. I'm waiting, let's say, while count equals to 0, one thread. What can happen that neither of this process can make any progress? So I'm getting a lock mutex, then I'm while count equals to 0, maybe initially it's 0. And I'm basically in this loop and I'm not releasing the lock. So why is it a problem? Okay, go ahead.
Because if you're not updating the counter at all, then you're just gonna get stuck in an infinite loop, right?
Yes, and to update the counter, what is the condition to update the counter?
You need to unlock, well, the counter needs to not be.
You need to get the lock, right? And you already grabbed the lock. One thread already grabbed the lock and trying to get this condition, but the other thread is ready to update count, and now count will become 1, but unfortunately it cannot get the lock. So yeah, so this is how they can get both stuck, right? So they are waiting for each other and no one can make any progress. So how can we solve this problem? So how can we solve it? Okay, go ahead. Different logs. Well, I'm not sure if I use different logs, then I may potentially have still data races, right? So can I use the same log and fix this problem somehow? Okay.
You don't need the lock in the beginning, just the one for the count, but you don't need lock.
Well, I kind of disagree with this because loads and stores can be reordered also, right? So there is a potential data race, right? If I don't, if I'm getting count outside of the log. So is there any way that I can still get count inside the log, but such that it will not be it will not get in a situation where I'll never release the log. Well, you can do, but let's say we're not using trilog. That's a special case, but yeah. I mean, anyway, what are you going to do? Busy waiting if I cannot get the lock? I mean, you still need to get the lock to read it. Is there any solution to that? Maybe not the best solution, maybe a little hacky solution. I guess the best solution is to use semaphores and conditional variables, which we will talk about later. But you know, like what can we do right now, right? Given that we are busy waiting here.
Why do you need lock?
Because we need to read counter. So counter can be updated by another thread. So, you know, so there are many issues with this. So if I don't get it under the lock, that means I'm gonna have a data race. So I can potentially have some stale value, loads and stores can be reordered. On like the compiler can actually reorder, the hardware can reorder, you know, especially with multiple cores. So in one core it can be 0, and the other core is going to be 1. We'll look at this example. Okay.
You check count and then you wait. You unlock it and then you wait some time and you relock.
Yes, so you get the lock, you go to while count 0, then you unlock, then you get lock again, and then you go to the second iteration, then you unlock and then lock again and so on, right? Okay, let me put it here. Okay, so Okay, so you will get count. Okay, while okay, so you have while count equals to 0, something like this, right? So you don't do anything, right? So you're just busy with it. So what you can do is this log, and I'm using ampersand because that's how pthreads will use it. Will pass a pointer, even though I don't show it on the slide. I'll do unlock mutex. Then lock mutex. I can put some sleep here as well. It's fine, right? So, but I can also skip it. And then I'm gonna go to the second iteration, and eventually I'm gonna unlock mutex. Well, it's a little hacky solution, but at least better than what we have right now. So you'll still read count while holding a lock. So therefore you won't have any data erase. But at the same time, you will allow another thread to proceed. So because eventually going to unlock the mutex, and hopefully if the schedule is fair, the other thread that was previously trying to get a mutex will be in front of the queue. So it will get the mutex before you get it second time. So because you unlock and then lock, but the second lock may doesn't mean that you're going to get it right away. So you may still because you are going to be, you know, the producer may be already requested the lock, so therefore the producer is already in the list, and only after this you come and then a request we're going to be the second in the line. That's how you can solve it. Again, it's not the best possible way to solve it because anyway, it's the best way would be to use condition variables and semaphores, which we will talk about later, but something just to keep in mind. Okay, so we talked about deadlock already, right? So yeah. Oops. So what is the other condition for deadlocks? Well, it can be tricky sometimes because you may not necessarily see it immediately. Like, but let's take a look at this example. And even though in this example the issue is kind of obvious once you look at it, in real life it can be more complicated because you may have some functions where you hide some logs, and you know it may not be obvious you know where this lock is and why is it causing a deadlock, right? But let's take a look at this example. We have one thread that's getting lock C and then lock A. That's thread 1, and the thread 2 is getting lock A and lock C. So the order of unlocks doesn't matter in this case because unlock doesn't cause any blocking. But the order of locks matters because every lock can potentially be blocking. So again, it can be the case that you have lock C, then some operations, and then lock A, and then on the second thread it can be lock A, some operations, and lock C. May even be, as I said, something that you don't even notice. Maybe you just call some function which modifies some buffer, and before to do that it gets a lock, and so on and so forth. So it's not necessarily something that it's immediately obvious to you. But at the end of the day, if we simplify it, we have this sequence. And it doesn't matter whether there's some operations in between or no operations in between, you can still have a deadlock. And you know, sometimes you may wonder, why do I need two locks? Well, again, there might be some resource that for which we need lock C and another resource for which we need lock A. maybe one buffer requires log C, another buffer requires both log A and log C. I don't know, something like that. So can you give an example where we have a deadlock here? Any ideas? Okay, go ahead. I'm sorry? Yes, yes. So you get log C in thread 1 and you get log A in thread 2. And maybe after this, threads were preempted, doesn't matter, right? What happened? Or maybe they had some other operations and got preempted, who knows, right? Eventually, they're gonna try to get log A and log C correspondingly in the other order, right? So the other way around. So now when thread 1 tries to get log A, it cannot get log A because it was already taken by thread 2. So when thread 2 tries to get log C, it cannot take it because it was already taken by thread 1. So now they are waiting for each other and will wait until the lock will get released, and the lock will never get released because we have to complete the critical section. Only after this we will release the locks. So, and therefore, basically what will happen, two threads will not do anything, they'll just get stuck and will be blocked. So CPU will be pretty much idle, not doing anything. So your program will hang. So that's what will happen with deadlocks. So now, does anyone know what the live lock is? Live locks? No? Yeah, so the key feature of deadlocks is that both threads will be idle. They will not be doing anything useful. I mean, it's not just they're not going to be doing anything useful. They'll be just idle. They'll be waiting. So with live locks, it's somewhat different. Yeah, so they will also not do anything useful, but they will not be waiting. They will be kind of busy waiting, right? So they'll try again, and so on, right? And eventually both threads will not be able to make any progress. So let's say we have an example with try lock. Maybe it thought that, you know, was not a good idea to get lock A. Maybe instead let's do try lock. We'll try to get a lock. If we are not successful, we'll just repeat it again. We'll just unlock, repeat it again, and so on. So what we'll do, we get lock C, we'll try to get a lock A. If we are successful, we'll exit, we are done, right? If not, we will sleep a little bit and then unlock C and then try to repeat the same procedure again. So now there is no issue, seems like there is no issue in terms of deadlocks because two threads are getting just one lock at a time. Like thread 1 is getting lock C and thread 2 is getting lock A. I mean, they're trying to get the second lock, but that's not causing blocking. It may cause only blocking for the first lock, but not for the second one. Okay, we have that, but still what may happen is that every time we repeat this loop, we get lock C, okay, we are successful. Then we try to get lock A, but we are not successful because maybe at that time, thread 2 was scheduled such that it got lock A at that time, right? And then while you were breaking from the loop and sleeping and then unlocking C, maybe exactly the same time it took for the second thread to figure out that it cannot get lock C. You know, maybe it was sleeping for the same amount of time and then again doing the same operation, unlocking everything, and then, you know, again ended up in the same starting condition, right? So where everything is again the same, and again they will never be able to complete. Okay, go ahead. I'm sorry? Yeah, so it can potentially get, I mean, due to randomness in the system, right? It's highly unlikely that in this particular example, it will take forever. It may be, you know, performance inefficient. I mean, maybe not very efficient in terms of performance, maybe the other issues, maybe it will get stalled for a while, right? but eventually it will probably get unvetched, right, at some point, because due to randomness. So sooner or later, maybe you will sleep one, nanosecond more or less, or whatever. And there will be some time difference. So I think in that case, that issue is unlikely to happen in practice, but there might be some more subtle examples where it's kind of going to be guaranteed to happen no matter what, right? So and then we will have a live lock. So it's not, I mean, after sufficiently number of after a certain number of operations, it will get to the state where it cannot recover, which it cannot recover from. At least it cannot recover easily just using some small random delays. So again, this is more like sometimes it's more philosophical issue. Can it happen in practice? For this particular example, probably not. But there is still some maybe worse examples where live lock can still happen. And no matter how many hours you're going to wait, it's still going to be a live lock. Okay, so the difference again for deadlocks, the key feature is that it's idle and the threads are not doing any useful work. For live locks, it's the opposite. They're busy, they're trying to do something, but they're not doing any useful work. So that's what a live lock is. So obviously, in your algorithm, probably you don't want to have deadlocks. So that's, I guess, one requirement we always have. One way or the other, we want to avoid deadlocks. So what, by the way, what is the way to prevent some deadlocks? Like, can we order like locks or something like this? Get it in the same order. So if we get locks in the same order, like A, B, C, and then I can get AB or BC or ABC, right, in that order, or AC. So if I preserve that order, then I should never have any issue like this. I mean, it's not always possible, but sometimes it's possible to preserve an order. It's certainly better than even than dealing with deadlocks. So now that doesn't necessarily mean that we don't have any other issues. We may, we may solve the deadlock issue, but still some threads will be starving. That means, overall there is some system progress. Some threads are making progress, but maybe one particular thread is starving. That means it's not making anything, right? So it's like trying to do something, like always someone gets in front of the line and it's unable to do anything. So it's like you go to office hours, some students still ask questions, right? So overall there is a global progress, right? So professor is answering some questions, right? But your particular problem is not solved, so you are kind of a starving thread. Now starvation doesn't necessarily mean there is some fairness. In terms of starvation, like you maybe go into a store and wait in a line to be serviced, and maybe by the end of the day they're able to service you. I'm exaggerating, but something like that. So in terms of starvation, there is no starvation. So you still have a finite number of operations, a finite number of finite time that you need to wait before you get serviced. In terms of fairness, maybe not so much, because maybe other people get in front of you, they are serviced first and you have to keep waiting, right? So it doesn't necessarily mean that it's fair. So no starvation doesn't necessarily mean that everyone is kind of in fair condition, like in fair manner. So, but sometimes you want to say bounded waiting. I want to have, I don't want to wait long. Like, I mean, I can allow waiting certain time, like maybe 5 minutes, but after this, I'm going to leave the store. I'm not going to be waiting in line, right? So something like this. So the same thing here. You will have some bound, and after this you have to be guaranteed to be serviced. So maybe the total number of clients that are currently there right now. So you'll wait for these people, but you will not want to have anyone in front of you who comes later. So obviously, at each point, it's becomes harder and harder to guarantee. So no deadlock is kind of something that, you know, hopefully most algorithms will at least attempt to do. Now with starvation freedom, it's a little bit tricky, you know, because again, in practice, you may say, due to randomness, starvation is unlikely, and maybe I shouldn't spend time designing some starvation-free algorithm. And you know, bounded waiting, I don't know, it depends on your kind of conditions, whether you want to have some sort of fairness or not. So you can also have some sort of traffic analogy for mutual exclusion. So for so what is the shared resource in this analogy with the cars? What is the shared resource? So every car has to stop right at the intersection, and then before it crosses the street. Okay. Yeah, the intersection itself, right? So that so that's the shared resource, like a lock in our case, right? So once the process is is in the critical section, no other can enter the critical section. So that is the analogy. So now in terms of progress, let's say one car comes and stops at the stop sign, right? And maybe other cars, hopefully it can go direct, like right away, but let's say it has to wait, has to wait its place in line. So what would be an example of starvation?
Everyone's stopping.
Well, everyone's stopping. It's like, okay, you can go. That's kind of a deadlock situation, right? So when no one goes, everyone is stuck, and they hoping that the other person will go. Yeah, that's kind of, but let's put that aside, right? So maybe like the first person who came, should go first, right? So, but then, what is the problem with starvation? Maybe one car crosses the street, but the other one is also maybe like red car is waiting to cross the street, right? But let's say yellow car has decided to go because it was first, so it goes first. But right after the yellow car, there is another car, there is another car, there is another car, and eventually maybe there is a red car is kind of stuck. So overall, some cars are moving from the intersection, so there is some global progress. But this particular red car is starving, right? It cannot cross the intersection. So that will be an analogy of starvation. And then maybe you can say, okay, that's wrong, right? I want to have some sort of fairness here. Maybe I'm gonna say, okay, I'm gonna wait at most 3 cars that are already in the intersection, and then I don't care about anyone else who comes later. And if you put this rule, then you are fine, right? So then you can have that kind of fairness condition. So far today we covered race conditions, bugs, swap instruction, pthread locks, examples with locks, deadlocks, live locks, and mutex liveness conditions. Let's actually go back to our example. And some of you ask, why do we need to get a lock while we are reading something and so on, right? So let's take a look at this example when memory reordering can happen. We have 2 threads, thread A and thread B, and let's say X and Y are initially 0. So in thread A, X is equals to 1, in thread B, y equals to 1, right? So that's what we're going to set. Then later in thread A, we're going to have A equals to y, and in thread B, B equals to x. So now, I mean, guess what? All possibilities exist. When A and B are zeros, A and B are ones, and A is 0 and B 1, and A is 1 and B 0. Everything is possible, potentially. Why is that? Well, if you look at 0, so by the way, the instructions can be reordered by both the compiler and hardware. So why does compiler can reorder instructions? Why compiler can reorder x and a equals to y? Because the way that compiler looks at the code, it just assumes you have like single thread, right, or something like this. It doesn't, doesn't know that something magically happens behind your back. So it's something that is changed, like y is changed or whatever, right? It looks at the y value is 0, then you set x to 1, and then a equals to y. So it can even can as well just set a to 0, right? A can be initialized to 0 because it just assumes that that was the initial value of y. Why not? Why can't we just do that, right? So because the compiler doesn't know about thread B when it looks at thread A. In fact, even if it's a pthread and it's a thread function, it will look at this code, it will have no idea that it's actually going to be multi-threaded. The compiler will not do any special steps here. So therefore, it can assume that x equals to 1 and a equals to y can be reordered, because there is no data dependency. Now, if there is some data dependency, if a equals to x, there is a data dependency. Then I need to first initialize x, and then a is going to be initialized to x. With data dependency, neither compiler nor typically hardware will reorder anything. But when we have no data dependency, no control dependency like this, then even the compiler can reorder things, because maybe it realizes that it's better to optimize x variable. I mean, it will better optimize some code if it initializes x variable later. Yeah, so, and certainly hardware can do that, and we will talk in a moment why hardware can also do that. But let's go back to our results. So how can we get A0 and B0? So the initial value is 0. So if thread A sets A to 0, yeah, so that's fine, because y was initially 0. Maybe this particular thread or this runs on a core which still doesn't have the the most recent value, or maybe it was reordered. So I can potentially just say, okay, is equals to 0 because y was 0, and so on. So 0 I can explain. The same for 1. I mean, then I can just assume x was already set to 1 and y was already also set to 1. Okay, so something in between when we have a equals to 0 and b equals to 1. How is that possible? Well, again, it can get reordered on one side, but not on the other side. So on one side, it can be, x equals to 1, a equals to y, and on the other side, it can be b equals to x and y equals to 1, right? And that way, because it was reordered in the second case but not in the first case, you can get 0, 1. And if you do the other way around, you get 1, 0. So the compiler reordering, that's something that is straightforward, because it can do that for to optimize performance, and the compiler doesn't know that you're running multiple threads, doesn't know your intent. It just sees some function and nothing special there. In terms of multi-core CPUs, we also can have a reorder. Let's say we have two levels of cache, L1 cache and L2. And in L1, maybe your private copy is saying, okay, X equals to 0, Y equals to 0. But maybe the results were not yet propagated to L2. So one core modifies it locally in L1, but L2 still has tail value. Even if L2 gets propagated, it still has to get to L1, right? So there is still some time before that happens. So we can easily get memory reordered here. So how can we solve this problem? Well, in C11, C++11, you have some way to control the so-called memory barriers. I mean, you don't have to use C11 for that. You can, previously was also possible using some assembly function, assembly instructions. So the way that you can do, if you just want to prevent the compiler from reordering, that's probably going to be the weakest one. It's also in C11, it's like signal fence or something like this. It's called signal fence. But it's not that useful because if the compiler doesn't reorder, it doesn't mean that hardware doesn't reorder that. Even for x86, where we have a strong memory, relatively strong memory model, it's still not sequentially consistent, and we still can have some stores that are reordered. So we still want to have some sort of hardware memory barrier. So for that, it will issue a special instruction like mfence in case of x86, and that will make sure that that the loads and stores are ordered in the way that you expected. I mean, it depends also whether you use memfence. There's some full fence. There's all load fence. There is store fence. For x86, you only typically want to make sure that your store operations are not reordered. For ARM, it's a weaker memory model, so we want to take care of more cases there. Yeah, anyway, just for your information that we have to, we can have some instructions that are reordered, but we also have some control to prevent that.